Hi, this is Vivek, and today we'll talk about how exactly to approach hard problems because many students come up to me and say that Vivek, okay, you can kind of solve hard problems. You have done a lot of preparation in CP. You have like kind of cracked ICPC, but then how do you actually think, or what is a systematic way to approach any hard problem that comes your way? Because I feel a lot of things people just kind of keep behind a simple term, practice is something that can be understood in a frameworkish way, right? So let's try to understand how can somebody think about solving hard problems. So let's suppose if a hard problem is thrown at me, how would I think about it, or what is the correct way to think about it, or how does the brain works for that particular problem? Okay. In this particular video, I'll take up this question: count paths that can form a palindrome in a tree. So basically, this problem I think came in a lead code weeklies last to last week, and this problem is something that I've seen before too. Like this had appeared in like placement tests of Uber online assessments. Exact same question. So I knew the idea, but then let's try to understand this problem from the lens of how would you approach it if you are somebody new and seeing this problem for the first time, right? Or what would it take, or how my brain would work, right? So the first thing that I will read in this problem is you are given a tree and it's rooted at 0. Okay, so it's a 0 index tree. And then you are given the parent array, which means you are basically given a tree structure in a parent structure that 0 is the root, and then you have a bunch of parent, like this is pointing to this is pointing to this, and so on. So you can build the tree from this parent array. And then for every character, like for the node number 1 to the parent is given by this character. Similarly, like the next character is given by the next index. So for 5, if you connect it to its parent 2, then the edge will have the character C. That's what is given, right? That the SI is the character between I and parent of I. So that's something that is given to you. S of 0 is just a dummy character to make the indexes work properly. Now, what we need to find is, given any particular path, we have to tell, can we arrange that in a palindrome? So let's suppose you have the path from 3 to 5. So the path will be AC, but it can be rearranged into ACCA, right? So it is fine, right? This can be rearranged, like a single A can be rearranged. A single A comma C 0 to 3 cannot be rearranged because A comma C can, no matter how you rearrange it, it cannot be a palindrome, right? But ACA can be done. So 3 to 2 is a solution, is a possible pairing, right? 3 to 2 is a possible pairing. 1 to 5 is a possible pairing. CAC, right? Then 3 to 5 is also possible, as we already have seen over here. And single characters are anyways possible. So we can count that it's going to be around 8. Right? So we have to count the number of such moves or such paths that exist. Okay. So how do you approach such problem when you see it for the first time, right? Let's try to think about that. Now, what I understand from teaching for more than 2.5, 3 years now, that problem solving all the way kind of boils down to building frameworks, tactics, forms, and concepts, right? When people say practice, they basically say that play the game, try to defeat monsters. Once you defeat some monsters with some help of editorials and all, or maybe yourself, try to collect these drops from those monsters and then use them to solve the harder problems next coming up, right? That's what the whole game is actually. You basically, every problem has these drops and you collect them to beat the next monster, right? That's all it is. Let me show you what exactly this is, okay? So as soon as I read this problem, the first thing that should be in my mind is a framework to attack such problems, right? The two words that I read is, there is a tree given to me and there is a path. I need to count paths, or I need to count the number of paths in such cases, right? Now, there are two ways I can think about this. For every node, I can try to query the number of paths, or I can just try to count the global path, right? So when you say u comma v, in my framework, there are two approaches for it. One is that from this u, I can try and count all v's, or I can try just global counting u comma v's, right? So it can be framed in a query way or a count way, in a global count way, right? Now, in a count way, you can try and use contribution of every edge or something, or every node maybe, or you can try to count things at their LCA, like every path will be counted at its LCA, something like that. Then if you try to use some sort of HLDs, it might be a path query, it might be some centroid technique, or some offlining of queries might be responsible for things. And I'm just trying to note down all general forms that exist for these kind of things. But again, when I see a tree plus path problem, this is what comes up to my mind. This is the framework. I need to just think about which one works the best way in this case. Okay. Then we think about framework 2. Okay, we need to think about path on trees, right? When it's a difficult operation like rearranging it to a palindrome, you think about, okay, how can you solve it on subarrays of an array, right? That's the first thing that you start solving, because paths on trees are equivalent to subarrays on array. Okay, this is the next level framework that you have, that how do you boil down a complex operation for a simpler idea first. So some path might be equivalent to some subarray, right? Bunch of paths possible. A tree can be just linear like this, and I can give you bunch of queries, a bunch of operations like, hey, tell me from this to this, this to this. So it's equivalent to having an array and just solving it for an array first. So if you solve a problem for array, then translating that to a path on trees is generally what you do. Okay, when you have a newer operation. Since we are seeing this operation for the first time, I'm assuming that you don't know this operation, right? How to model this. Okay, now the next thing that you need to understand is I need to kind of solve this reduced problem, that given a subarray, I need to count the number of, like, find out whether a particular subarray is palindrome or not, or count the number of subarrays that are palindrome, that can be like rearranged to a palindrome, right? So what is the concept that we need to understand over here? Okay, the first thing that we need to understand is, when we need to check palindrome, we are basically talking about some structure which is either odd length or of even length. When it's odd length, this and this needs to be same, this and this needs to be same, this and this needs to be same, and this can be anything, right? When it's an even length thing, this needs to be equal to this needs to be equal to this needs to be equal to this, right? Now, another phrase that is given to us in this problem is rearrange to a palindrome, right? When we can rearrange, whatever we put over here, if we have that same character available, we will put over here and make this condition satisfy. Whatever we put over here, we can put that same character over here if it's available and then make it satisfy, right? So as long as we have two elements of same type, we can just put them at the corresponding places, and that place will satisfy the criteria of being a palindrome. So what can we have in such cases when we need to make sure that things can be rearranged, right? Whatever is over here needs to be present over here too. So there has to be some element which is available twice, right? Another element which is available twice, right? Another element which is available twice. So every element either needs to appear twice. In that case, it will be we can always rearrange to an even length, or else there would be some x, some y, some z, which will appear twice, 2 times x plus y plus z. When I'm writing this, not an expression, it's basically just saying that x appears twice, y appears twice, and so on. And then there is some star character which we don't know, which can be anything like a, b, c, d up till z, anything, right? Plus some star character which can be anything. So all of the things appear twice except one character, right? So any string, when we can rearrange it, can become palindrome if either all of them appear twice, all characters appear twice, or one character appears just once extra and everything else can be said to be appearing twice, right? That's the simple level of reduction that we can get it to. And now we have a simple concept or observation that if you just simply try to find the frequency of the characters that are present in that subarray, right? When you have to rearrange them, the frequency, the parity of the frequency needs to be something that you can say from this equation, that either only one character will be appearing odd times or all characters will be appearing even number of times. So only, or I can say odd frequency less than equal to 1. That is the single condition for the set to be possible to be rearranged into a palindrome, right? That is what you observably see for a particular problem. Now, if you have never seen a rearranging problem of palindrome, this might be difficult to get on the first go. But then again, I think this is a fairly kind of direct observation that when can you rearrange something, right? You try to break down the atomic operation that you are given, atomic condition that is given, right? So odd frequency should appear less than equal to 1 time, either 0, which means everything is twice. That's fine. We can rearrange it in an odd manner in an even palindrome. If one thing appears as an odd stuff, we can just put it over here and the rest would be paired up together, right? So that's the simple thing. The odd frequency should be less than equal to 1. Now, two very important things. We have an odd over here. Like, one thing to understand is we have an odd or even concept coming into picture, because no longer frequencies matter, but odd frequency, right? That is one thing. Next is it should be less than equal to 1. Okay. So that's the final observation or concept that we build on top of it. Okay. From there, we go to tactics 1. Okay. For a particular subarray, we need to find whether that subarray has a number of odd frequency element less than equal to 1 or not, right? So what we can do is we can use a very simple tactics that is very common in strings, that in this part we need to find the frequency of A, B, C, D and so on, right? That is the first thing that we can try and see, that we need a frequency of everything, and we can see that how many of them are odd, right? That's what we need to find. So when we have strings, we have 26 characters only. That's the first tactics that we use, that when we have only 26 characters, maybe some sort of prefix sum can help us. Maybe some sort of prefix sums can help us, which will help us build, like for a we can maintain a prefix sum, for B we can maintain a prefix sum, and we can get in the range how many numbers have, how many positions have A, right? That is something we can directly do using prefix sums. So some sort of 26 into n structure we can build, and this is a tactics that you need to know so that you can find the frequencies very fast in a range, right? Now you might ask me, Vivek, how will you come up with this tactics, right? No, you cannot, right? That's what I said. You pick up these drops, right? You have to know prefix sums before solving this problem to understand this idea. If you're, even though this is not the final idea, if you're thinking about this tactics, you have to know prefix sum before this, right? So it's all about collecting these tactics. Tactics number 2, that can be an approach that we try to count every character's frequency, and then we see how many of them are odd, and then we can check easily. So every range we can check very, very fast, right? That's a tactics that can help us in this problem. Maybe I'm just thinking about these kind of things while I'm solving the problem. Next thing that we can use is, hey, I only care about odd frequency. I only care about being odd frequency, right? So if you truly think about it, the total count doesn't really matter. Just the parity matters, right? So a very, very common technique that we use in such cases when you have to only maintain characters or parities is convert it to present or not present, right? So what we can do is we can build some sort of prefix XOR, okay? We can encode every character into a mask and then take a prefix XOR. Now this is another technique that you will need to know about. If you have never seen prefix XOR before, there is no chance that you can solve this problem, right? There's no chance that you can solve this problem. Prefix XOR is basically, if you want to solve the XOR of this particular range, you will have to know how to find that quickly by just taking XOR of these two ranges. If you take these two XORs, we know that in XOR you have a property that if something is counted twice, they get cancelled off. So only this much will remain, and you will get the XOR of all these things. And it should be such that A and B don't interfere with each other. What we will do is we will encode A as, let's suppose, A is present, A is present, A is present, A is not, B is not present, B is not present, B is present, not present, present, not present, present, present. C is not present, present, not present, not present, not present, not present, not present, not present. D is not present over here. So D is only present over here. Rest all will be 0. So this is simply converting every position into a mask so that we know which character is present over there. And then what we want to find is what is the parity of, let's suppose, this range, right? So what we can do is we can build prefix XORs. Like, hey, if you build prefix XOR, what you will have is 1 0 0 0, then this XORed with this, so it will be 1 0 1 0. This XORed with this, so you will have 1 1 0 1 1 1 0. Then XORed with this, so 0 1 1 0. XORed with this, so 0 0 1 0, right? And you can see that till this much, B appeared twice, A appeared twice, C is only odd number of times, so we have only C as odd parity. Again, A appeared once, so 1 0 1 0. B appeared over here, so 1 1 1 1. Oh, sorry, not over here, and then 1 1 1 1. Okay. Now, if you ever have to find for any range, like say over here, find the parity of the things over here. So it will be as if like you are trying to find the XOR of these elements in the original one. And you can see that that's nothing but this XORed with this, which is nothing but 0. If you XOR these two things, they would be 0, which means everything appeared even number of times, and you can say that this can be converted into anagram. So how can you think about this particular thing? Prefix XOR, if you have not seen these tactics before, you cannot solve this problem. As simple as that it is. Okay. That's what people say as practice. Collect these tactics. Okay. When people say practice, essentially they mean that collect these tactics. Khatam. Nobody solves all questions in contest without seeing all of them before. Okay. If I solve a problem in contest, for at least for lead code and online assessments, all these things, 100% of the questions, or at least 80% of the questions I've seen before, 90% most probably for me. But you should be like in a place where you have seen all of these tactics, strategies and frameworks that exist, or else you will not be able to solve it. That's it. Okay. People think that it's about thinking, it's about IQ and all. It is there to some degree. It's about connecting dots, but it's more about how much of tactics have you collected till now with practice. Okay, that's it. That's all it is. Believe me. Okay. Now it's about tactics, how much of you have collected and how good frameworks have you picked up from others. That's what I think it's all about. Okay. So now we have a tactics key. Acha, we can try and map these characters into bits and then maybe try taking a XOR, and that will help us find whether something is possible to convert into an anagram of, whether something is an anagram of a palindrome or not. Basically, anagram means we can rearrange characters. Okay. Then we come back, we try to see, okay, how will we solve this problem? We had this framework, right? That, hey, tree and path problem, either counting and queries. Queries seems difficult because for every node, if you try to query, there will be so many nodes. You can do all u comma v, but then it's very difficult. Instead, we'll try to count. For count, we can try and contribution of every edge. No, because we cannot really find how many paths this edge will be part of and will make it palindrome. So it's very difficult. Contribution of node, super difficult to do. In this case, edges are important. At LCA, that is something simple, right? Because over here, this is a very standard strategy that when you have to count total number of u and v paths, you try to count things at their LCA. That, hey, u, v, you try to count how many paths pass through this, such that it comes from one of the nodes and goes into another child, and then we try to count all such valid paths, right? That's what we try to do. Say this particular thing over here, okay? If we want to try to kind of check the valid paths, right? What we can try and see that, hey, this is the, let's change the color. This is the LCA, okay? Now, if I try to take something like, okay, from over here, I'm trying to go till this LCA, and then there is another path on some other child, which is similarly over here, okay? Now, when we merge two paths, this path contains CAD. It's like a collection CAD, okay? This path contains a collection DC, okay? Now, when you merge, it's like summing up their total frequencies, right? Because we can anyways rearrange. So it's like summing up their total frequencies. So what we can do is we can simply assume that the final like path would be CADDC. Okay. Now, in this case, we already came to a conclusion, right? That when you have such things, right? When will we have an odd frequency? When for that particular set, the bits will look something like all zeros, which means every frequency is even number of times. Okay. If you take XORs and all, if you have all zero, which means everything appeared even number of times. Okay. Or exactly one of them needs to be 1. Rest all would be 0. Something will be 1 and rest all needs to be 0, which means one odd frequency. Okay. This is basically giving us the parity of frequency. Okay. XORs is going to give you the parity of the frequency because that's how XORs work. Okay. Now, this is how you kind of build this. We want to find the parities of individual numbers over here. Now, if you want to build the set and then merge, it is difficult. What we do is we maintain masks. Okay. So for this node, you know that this path will have a mask of, let's say 1, A, B, C, D. This will have A is present once, odd number of times. C is present odd number of times. D is present. So this is the mask. This path has some sort of DC. So this would be A and B are 0, 0, and then C and D are present. So 1, 1. And when you merge them, it's like an XOR of these two things, because If they are both odd, their sum will be even. If they are both even, their sum will be even. If they are odd even, then they would be odd, right? So it's like an XOR of these. So you will finally get 1 0 0 0. It turns out that only one of them is odd. So we can, in fact, this cancels, only one of them is odd. So we can convert this into palindrome. So it now kind of comes down to, for every node, you try to find out how many like paths that go inside that subtree, which such that two of them merge together to give you a XOR of either all zeros or a single one. Then there is another level of tactics that you can use in this problem, which is, hey, if you have, say, for this particular node, you can calculate the subtree things like, hey, what is the XOR of bits from here to here, over here to here, over here to here, over here to here, and try to merge them. But then you will have to do that for every node, right? It turns out, just think about a single path, okay? Let's say something like this, okay? This path over here. This has some 1 0 1 1 0, something like this, okay? This particular path, let's suppose, has some 1 1 0. I'm just assuming there are more nodes. Of course, it's like something like this, some number, right? I don't care about that right now. And whatever will be the XOR will be the combined XOR of the path, because we have to check the parity. Now we can actually just add more things back to the root to make sure that these are simpler to calculate, which means even if let's suppose this path has an XOR of X, right? All the numbers, like this is C, so this will contribute to the Cth bit in the number. This is A, so it will contribute to 8th number. So this path has a bit of, like, has a bit mask of this, okay? Now, from this particular path, from this root, if you try to get the total value till the end, it will be nothing but this number XOR X. So let's call this as Y, let's call this as Z. From root to this A and this B, root to A will be nothing but X XOR Y. Root to B will be nothing but X XOR Y. And root to LCA is given to be as X, like we are assuming that it's X. So now if you want to find the XOR of path from A to B, a very simple strategy that you can use is just XOR these two things. Just XOR these two things, because if you XOR these two things, X will cancel and you will get Z XOR Y, because if anything gets XOR twice, it gets cancelled off and you will get the XOR of the full path, right? So this is where you try to see that, okay, maybe just calculating the masks from the root to every node will solve the problem, because even if you combine these two things calculated from the root, whatever will be the path XOR from LCA to the root will get cancelled when we XOR them. So it's just it's equal to saying calculating just these two values is sufficient, because when you XOR them, you get equivalent value of the actual path. And that's it. That's the final tactics used for this problem to make it very, very simple to code. That, hey, from root, find every node's like path from over here to over here, over here to over here, every node's bit mask, and then see how many of them can be combined together to give a mask which has only 1 or 0 bit 1, right? So we use this concept that we can add this in the DFS. Now we use a concept, which means you need to know this thing when you learn DFS, that you can add more properties while traversing. This is something you'll have to see in a problem, only then you will know that you can use these kind of things, okay? And this is what I think people miss on learning. I mean, this is what you need to learn. It's not about solving hundreds of problems. If you don't see these concept tactics, if you don't extract them out, you'll never be able to solve any hard problem. I can guarantee you that, okay? Most of people who become good at solving problems extract them without like explicitly mentioning them, right? They extract these ideas without mentioning them, right? But these are things that you can actually learn, right? That, hey, from the root, I can, while I'm doing a DFS till a node, I can maintain an auxiliary value that it will tell us the XOR of the bits that I've seen till now. Like let's suppose A, B, C I've seen once. And then when I go from over here to over here, in DFS we go to a child, right? So in the DFS child, when I will call DFS of the child. Its parent will be this node, okay? I'm not writing the parent. You can put more values, like you can put the parent and all. But The main thing is this will also needs to be translated, that it was 110 till over here, and then you have an extra A. So that A bit needs to be flipped now. So you will have 0, 1, 1, 0, dot, 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 right? A, B, C, D, right? This kind of thing needs to be maintained. And this is something you can do while you do DFS. Now, if you know this, then you will be able to code this also very efficiently. This is a concept that you should learn while learning DFS. Let's go back and recap. A tactics that, hey, when you have to XOR, maybe XORing from LCA to both sides is same as XORing to root. Another tactics that you should have been seen before if you're solving this problem. Okay. Form 1, I think you need to understand that you're trying to count at LCA, and that's the best strategy for this. That's the form of this problem, right? Tactics 2, how to convert the numbers to bits and stuff, right? Tactics 1 was basically you can try and use prefix sums to get the actual counts also, right? Possibly. A concept and observation is what, how did we convert this and stuff, right? So let's go down and let's kind of complete this. So final idea is basically we start from root and we maintain, hey, what's the bit mask till this much? It's just 1 0 0 0. A seen once, B 0 0, B C D. Okay. So I'm assuming that 4 bits maintain the parity of A B C D till the root. Over here you have seen 0 1 0 0. You have seen B once. Over here till this much, whatever is the parity, you add this. So you get 0 1 1 0. Let's add some character over here, let's say A over here. So it will get 1 1 1 0. Okay. Over here also 1 1 1 0. Okay. Over here it will be 1 1 1 1, because this with including this one bit, flipping this bit. From over here, flip the dth bit, 0 1 0 1. From this, flip this bit. Let's suppose 1 0 1 1 1. And from over here, if you take this node and this node, you see this. From over here, even if you take, these are the masks till the root, right? Even if you take the XOR of these two, you will be left with 1 0 0 0, which means you have only an extra A, which is true, because if you would have taken the path like this, the extra thing would have been only A. So you can use these numbers to check if two numbers have like a single bit difference or not, and that's something we can do with a single hash map. So if I just show you in code, let's try to trace the code as well. I just wrote the code because some people told me, if you please write codes to explain things. So this is a hard problem. I have already told you this is a hard problem, but I just wanted to explain things in a way ki, how do you learn? How do you solve these hard problems? Is it even possible to get to that level? The simple idea is you need to collect these tactics. If you haven't seen these tactics before, you will not be able to do it. Okay. You should have seen forms. You should have built that framework for yourself by practice. Okay. Then only you will be able to solve this problem. As simple as this is, or else you should have seen this same question before. Okay. So over here, you basically from the parent array, what I've done is I've built the graph. This is a very standard thing, right? You build the graph from over here. Then what you do is you do a DFS, that DFS of node, its parent and the XOR till this point, the XOR value till this point. So you save the XOR value, go to its child, but while you go, like when A is over here, I convert it to 1 0 0 0. Okay. This is the 0th bit, 1 bit, 2 bit, 3 bit. So I'm converting every character A minus A bit shift. If it's B, then it will be 1 shift. If it's C, it will be 2 shift. So I'm keeping that in the edges, and then accordingly, I'm just taking the XOR of the path till wherever I am right now. And then while going to the child, I'm adding the next edges path also. Next edges XOR also. Flipping that bit basically. So in that case, what will happen is I will save the XOR value to every node from the root, have a simple frequency map, go through the answer. For any particular node, go through all the nodes, see how many times. So if you are at a node which has some XOR value of X, okay, let's assume that the XOR value till this root till this is X, okay. So anytime before, if you would have seen some XOR value Y such that these differ in exactly 0 or 1 position, then you have a solution, you will have a path, okay. So what we do is we find out how many times have you seen that exact same XOR value, and maybe change in exactly 1 bit. So I go through all 26 characters and see whether one of the bits changed has appeared before or not, and how many times has that appeared. Add all those nodes count, and then include the current node in the count map of how many times have you seen this XOR, so that next nodes can find this node, right? That's simple. I mean, that's how this can be solved. And technically, I don't see anybody solving this without understanding the underlying tactics. If you have not seen these things, you will not be able to solve it. Okay. That's how a lot of competitive programming is. I mean, people think that it's all IQ and all. No, I don't think it's all IQ. You have to have seen these tactics or forms before. You should have seen the concept while preparing. You can add auxiliary informations and all, and then only you will be able to solve such problems. Okay. So that's, I think, was the final like idea, that when you are solving problems, try to go beyond remembering that problem to abstracting them to the phase of building frameworks for you, that how will you approach such problems next time. What tactics did you learn in this? Like prefix sums itself is a tactics, right? Converting it to bit mask is a tactics, right? XOR till root kind of cancels till LCA, that's a tactic again itself, right? Forms are okay. How do you solve this class problems, right? As I told you, in this case, we solved at the LCA. We tried to count it at the LCA. That was the form of this problem. And then concepts like when you are learning DFS, BFS, all these things, you need to know the different variations that are possible with that. Okay. So that's, I think, what I wanted to cover in this particular video. A quick trailer of how you can solve such harder problems. How are people able to solve it? In fact, that was my main agenda, right? If you learned something, I mean, I understand this problem is tough. You have some idea now. Try to do it on a notebook and then solve it yourself once after this video. But then I hope you could get an idea ki how to actually solve problem. How are people becoming good with practice, right? This is what people say when they say practice. Learn these things. Okay. Now try to learn and grasp these things as you solve problems. And I will try to make more and more videos where I try to explain you these kind of things for different topics, different ideas. And I hope that will help you all to grow further in this domain. Okay. That's all from my side in this particular video. See you in the next one. Bye-bye.